Picture a transit system that looks like it came straight out of a science fiction film. A train carriage hangs 30 feet in the air, completely upside down, gliding silently beneath a steel track. It touches nothing. It simply floats. Now imagine someone cutting power to the entire city grid. Every light goes dark. Every screen shuts off. The train does not fall. It stays locked in place, suspended exactly where it was. This is not a concept drawing or a computer animation. It is a real experimental system that is operated in a Chinese county called Xingguo, known as the Red Rail. It is a suspended magnetic transit line that uses permanent magnets so the vehicle can remain levitated with essentially zero electricity. Traditional magnetic trains in Japan or Europe consume large amounts of power just to push the train away from the track. They rely on electromagnets. If the power fails, gravity wins. This Chinese design keeps the vehicle floating without continuous electrical input for the levitation itself. If you enjoy videos that dig into unusual engineering, please hit the like button. These take real effort to research and produce. Subscribe so you do not miss the next one. The principle inside the red rail is not magic. It is careful physical engineering. Instead of using electrical coils to create a temporary magnetic field, the engineers lined the track with rare earth permanent magnets. Think of the magnets that hold a heavy calendar on a kitchen refrigerator. They need no battery. They never turn off. They simply stick. The red rail scales that same idea up to support a passenger vehicle weighing several tons. Because the train hangs underneath the track, gravity pulls the car downward while the permanent magnets push upward against the supporting arms. The two forces cancel each other in a stable balance. The vehicle hangs in midair at almost no ongoing energy cost for the floating itself. A small amount of power is still needed to move the train forward along the line. But the expensive part of conventional maglev keeping the vehicle levitated is largely eliminated. Once the car is hovering, pushing it forward requires relatively little effort, much like sliding a puck across a smooth air hockey table. There is almost no friction, no heavy steel wheels grinding against rails, and therefore far less mechanical wear. This raises an obvious question. If a train that floats with almost no power for levitation is possible, why is there not one hanging over the streets of Los Angeles or Chicago? Why did Europe, with its long experience in high-speed rail, not build one first? The answer has less to do with pure engineering cleverness and more to do with access to the materials that make the system practical. To create permanent magnets strong enough to hold a passenger carriage, ordinary iron is not enough. You need a rare element called neodymium, combined with iron and boron. The resulting magnets are among the strongest permanent magnets known. A piece the size of a hockey puck can lift hundreds of pounds. These magnets form the core of the red rail's track. China currently dominates the global supply and processing of rare earth materials. Controlling the large majority of refined output, the United States has some deposits, including in California. But the difficult, chemically intensive step of turning raw or into high-purity magnet material is concentrated in China. Building an equivalent domestic supply chain would require years of investment and new industrial capacity. When American planners look at a permanent magnet-suspended train, they therefore see both an interesting technology and a reminder of material dependence. Traditional electromagnetic maglev systems are power-hungry. Electricity must continuously energize heavy copper coils to generate the field that lifts the train. Cut the power and the field disappears. The train settles onto the guideway. The system works well but carries high operating costs. The permanent magnet approach removes that continuous electrical demand for levitation. The magnets simply exist and exert force. The engineering challenge then becomes designing the geometry so that the downward pull of gravity and the upward magnetic force remain in stable equilibrium while the vehicle moves. Chinese researchers at institutions including Jiangxi University of Science and Technology developed a suspended configuration for the red rail. An arm from the vehicle wraps around the rail. Permanent magnets on both the arm and the rail repel each other, keeping the car suspended. With no physical contact, there is almost no friction and very little mechanical wear. Maintenance costs drop. The experimental line in Xingguo is only about 800 meters long and operates at modest speeds around 50 miles per hour, suitable for short urban hops rather than intercity travel. Construction cost has been reported as roughly 1/10 that of a conventional subway in some comparisons, partly because the elevated structure can use lighter supports and avoids deep tunneling. Hanging a train upside down looks dramatic, yet from an urban planning view, it solves real problems. Ground-level streets in dense cities are already full. Widening roads is rarely practical. A conventional elevated railway requires heavy pillars to support the weight of trains running on top of the track. By suspending the vehicle underneath, the center of gravity is lowered and the structure behaves more like a pendulum, which can be inherently stable. Lighter support pillars become possible, saving steel, concrete, and money. The line can be built above existing roads without tearing up the street for years. Once the vehicle is floating, the absence of wheel-rail contact eliminates the constant replacement of wheels, axles, and brake components that conventional systems require. For short-distance urban routes, the combination of lower construction costs, lower energy use for levitation, and lower maintenance is attractive. The contrast with many large American transit projects is stark. Expanding a few miles of subway in New York has cost billions of dollars per mile. California's high-speed rail effort has faced repeated delays and budget increases measured in tens of billions, with passenger service still years away. American cities often spend long periods navigating permits, land acquisition, and legal challenges while building systems that still rely on steel wheels on steel rails technology more than a century old. The Red Rail's experimental line was erected far more quickly and cheaply by comparison. For a driver stuck in traffic or a rider waiting for a delayed train, the difference feels concrete. The United States once led the world in rapid infrastructure construction. Today, many projects struggle with cost and schedule while other countries deploy lighter, more specialized systems. Yet zero electricity for floating does not mean zero cost overall. The permanent magnets themselves carry a heavy environmental price. Rare earth elements are not especially rare in the Earth's crust, but they occur in low concentrations. Extracting usable material requires mining and crushing large volumes of rock, then processing it with strong acids and solvents. The process generates acidic wastewater and other toxic residues that must be managed carefully. Decades ago, the United States produced rare earths, including from the Mountain Pass mine in California. Stricter environmental rules and higher compliance costs made domestic production less competitive. China accepted larger environmental burdens for a time, built processing capacity at scale, and came to dominate the refined supply. The silent, clean-looking float of a permanent magnet train therefore rests on an upstream industrial chain that is anything but clean. The environmental cost is paid far from the city streets where the train glides. Those same neodymium magnets appear in many other critical technologies. They are used in the motors of electric vehicles, in the speakers and vibration systems of smartphones, and in medical imaging machines. Military systems also rely on them radar sensors, actuators, and other components in advanced aircraft and precision weapons. A single advanced fighter can require hundreds of pounds of rare earth materials. When one country controls the large majority of refined supply, the rest of the world faces a strategic vulnerability. The Red Rail is a small urban experiment, yet it demonstrates the practical use of a material that underpins far larger industries. If export restrictions were applied, assembly lines for electric cars, consumer electronics, and defense systems could face shortages. The floating train therefore functions as a visible reminder of material leverage as much as a transit prototype. Even so, the technology has clear limits. The Red Rail is not a high-speed inner-city system. Its top speed is modest, around 50 miles per hour, making it suitable for short urban segments rather than long-distance travel. Lining many miles of track with high-grade permanent magnets is expensive, even when the material is relatively accessible. Stretching this system across hundreds of miles between major cities would drive material costs to impractical levels. The design is therefore best understood as a specialized tool for congested downtown corridors or tourist routes where quiet operation and low maintenance matter more than speed. It is not a universal replacement for subways, light rail, or high-speed lines within its niche. However, the combination of passive levitation, reduced friction, and lighter elevated structures offers real advantages. The broader lesson is about who controls the physical ingredients of advanced technology. For years, many Western economies focused on design, software, and systems integration while assuming critical materials would remain available on the open market. China invested in mining, processing, and the downstream manufacturing that turns those materials into finished components. The result is a supply chain in which one country holds a dominant position in the refined form of several strategic elements. Rebuilding alternative capacity elsewhere is possible, but slow and costly. It requires new mines, new chemical plants, skilled workers, and acceptance of the environmental trade-offs that accompany extraction and refining. Until that capacity exists, Technologies that depend on high-performance permanent magnets, including certain forms of magnetic levitation, remain tied to the existing supply chain. The experimental red rail in Xingguo will not by itself transform global transportation. Its value lies in demonstrating that passive magnetic levitation using permanent magnets can work at passenger scale, that suspended configurations can reduce structural costs, and that the materials enabling the system are concentrated in a single industrial ecosystem. The train floats quietly above the street, requiring almost no power to stay aloft. The magnets that hold it there are the same class of materials that power electric motors, medical scanners, and advanced sensors. The floating vehicle is therefore both a local transit experiment and a visible signal of deeper industrial realities. If this look at an unusual piece of engineering and the materials behind it was useful, hit the like button and subscribe so you catch the next deep dive. Turn on notifications if you want to be first to see new videos. Related videos are on the screen if you want to keep watching. Here is a question for the comments. Do you think countries outside China can rebuild rare earth processing capacity fast enough to support their own advanced manufacturing, or has the current concentration of supply already locked in a lasting advantage? Let me know what you think!